Okay, so we're back again. I was requested a while back, just a couple weeks ago, to do a video on the Tesla coil. So I figured I would. So here's a video on the Tesla coil. Now, I thought in a lot of ways, I don't know why this person was that interested in the Tesla coil now, because the Tesla coil is very cool, don't get me wrong. But there's other videos on the Tesla coil. So part of what I try to do on the channel is share things that are more uncommon or something that's interesting, right? Not to say that the Tesla coil is interesting. It is interesting, but it's not that uncommon. So there's plenty of other videos that you could find this kind of material on, but it is a good kind of introduction into, I guess, AC electronics. I'll do it, and we'll just have a brief walkthrough over it, and we'll kind of talk about what's going on. So, and there could be some models that use DC circuitry or within a Tesla coil, but typically it's going to be AC, and you'll kind of see why here in a second. So what's the difference between AC and DC? Okay, so AC is alternating current. AC is what we're mostly used to because that comes out of our sockets, and that's how we power things. DC, though, we use a lot today because of the 5-volt metric that powers most of our stuff because of semiconductors, right? Like all your phones and everything, it comes out at 5 volts DC. Okay, so this is just a rough schematic. It's basically just a diagram of a general Tesla coil. It doesn't have any values on any of the components, and part of the reason for that is a Tesla coil is it's kind of more like an experiment. It's not that technical of a device. It's kind of just, it's there to prove basically Tesla's theory on air core transformers, which is what this is. So if we look here, I wish I had maybe I can save this image. Test. I don't know. Let's see how this will work. I'll do it like this too, maybe, just in case. I just had the idea that I should probably put this in paint or something, so I can draw while I'm talking about this. So hold on a second, I'll be right back with you. Okay, I'm back. So we got it in paint here, so I can annotate a little bit here. So a Tesla coil is basically just an air core transformer. Now, why do we have to say it's an air core transformer, not just a transformer? Well, because most transformers are iron core transformers, and that's what we have here. Okay, this is a high voltage transformer that says here, and you can't really tell that by anything. You would just know that you would assume that by the operation that you're trying to facilitate. Another quick note is that this high voltage transformer could also be a low voltage transformer if you just ran it backwards. So let's say this transformer had a 120 volt primary and it had a 1000 volt secondary. Okay, let me move this over here. If it had a 1000 volt secondary and 120 volt primary, well, if we put 120 volts from this end, and because of electromagnetism, because this coil here, which is smaller, is close enough, even though it's wound by this iron core, and partly why it's on that iron core is to hold the windings. it's wound into this iron core, and on the other side of that, again, this is just a visual representation. This doesn't mean that the actual barrier or distance from this coil to that coil is actually that large. It could be larger or smaller, but at any rate, this coil is close enough to this one that the energy from here will transfer over here. But not only that, not only will it transfer, but the voltage on this coil will increase because there's more windings on this side. Okay? Because there's more windings over here, this is what the illustration is showing you, that this is a step up transformer. Okay? This is just a step up transformer. A transformer like this is typical in your everyday microwave that will have 120 volt input and like 1,000, I think it could be even a 2,000 volt output. Okay, now that voltage, if you say, oh man, 1,000 volts, that's a lot, it is a lot, but you remember that it's going to be at very low amps most likely. And if you have a transformer that is high voltage and high amperage, then it's going to be very, very big, because the coils get the size of the coil wire has to be larger in diameter to pick up to transfer current. Okay, so 1,000 volt transformer that carried 1,000 amps would be something like you would see in a substation, right? When you go by a substation, you'll see those transformers there that have fans on them and all kinds of things, and capacitors and coolers and all this stuff. Is because they're very large and they have oil in them to cool down. They're just because they're very large, and the reason why they're very large is not because they're just carrying something like in the order of like 12k volts, but they're using those substations to transfer energy to, communities and residential areas. And the typical residence, at least in North America, has anywhere between 120 to 200 amps. Okay, so it's supplying a ton of amperage to various places. So the wires have to be very large. Okay, the core of that transformer is going to be very large because the winding on that transformer is going to be very large, because it's going to be, when I say large, I mean thick. The thickness of the wire is going to be very large because it's transferring that much energy. But again, as I said before, this is a step-up transformer because of the way it's going, because it's going in this direction. If we made it go the opposite direction and inputted 1,000 volts, that means we would get 120 volts out on this side, because then it would be a step-down transformer. That means all the energy from this side would transfer electromagnetically to this side, and then we'd have 120 volts. Okay, I hope that is simple enough. That is a little intro into AC circuits and transformers. Okay, now that's what this whole circuit is based on, is that kind of theory. Oh, there we go. Now there's a little bit more to this that gets interesting. So I'll go from the high voltage transformer, and then we'll go to the Tesla coil, because what we want to figure out is, again, why is this called a high voltage transformer, just a regular transformer, and the Tesla coil, which is this here. The Tesla coil really is just this. This is really the Tesla coil. The Tesla coil is this and the toroid on top. Okay, this is the Tesla coil. This whole assembly here. But why is this called an air core and this is called a regular transformer? A regular transformer uses iron. This is called an air core transformer because there's nothing in between. If you see here, there's no two bars. These two bars in a transformer symbology is the iron core. There is no iron core here. Okay, it's an air core transformer, and that was Tesla's whole idea. It's like, okay, you can transfer energy through the air, essentially. Okay, this is an air core transformer. Okay, now there's a lot of debate about this, or people are like, why don't they have wireless energy and all that stuff? Part of the reason, and you'll see this if you ever build a Tesla coil, So having high voltage like this that floats around the air ionizes the air, and it makes it volatile to breathe in. So if you ever do make a Tesla coil, you will see yourself that if you stand too close to it for too long of a period, especially depending on what kind of material that you're using, like on the wires and stuff to make the windings, it's going to get uncomfortable. You might get nauseated because you're breathing in that ionized air. So it's actually not that comfortable, and there's some safety measures to be taken place when you're using a Tesla coil. It's not that friendly in a lot of ways. Most of the time, you build ones that are pretty low voltage, and what I mean by low voltage, anywhere between 1K and 5K. Which again sounds like a lot, but the whole idea is that this thing doesn't move a lot of current. So it doesn't move a lot of current, and then it's at very high frequency, and that's another thing that I'll show you here. Okay, so that's one of the primary elements of the Tesla coil, is that it's an air core transistor or an air core transformer. As you can see, it's depicted to have a little bit of windings here. It just has 3 loops here. Again, this is not an actual depiction. It's not showing you the actual ratio of windings. It's just showing you in principle, this side has very little windings, this side has a lot of windings. That's all it's showing you. The same thing with here. This side has a lot of this side has a little windings, this side has a lot of windings, right? It's just a general depiction. It's not showing you ratio, and like I said, Tesla coils are usually made for entertainment, so most people are not calculating necessarily, how many windings. They're just going to know that, hey, if I have, I don't know, 10 windings on here, I'm going to have 100 on this one, more than that. I'm going to usually when you make a Tesla coil, you find an object, you get like a 2-inch pipe, and you get some thin coil, and you just wrap it around there as much as you can. You don't let it overlap or anything like that, because you want it to be smooth, so the electromagnetic electricity can travel up towards the toroid very smoothly. Okay, but that's kind of that's the principle around it. So air core transformer, it has a primary. This can be kind of misleading, because this primary is not like the winding on this primary. Again, this is an air core transformer, so what happens on the Tesla coil, and I'll show you this in another picture, is the primary winding on the Tesla coil side is usually some kind of winding that sits at the base of the Tesla coil, like this, and then the Tesla coil itself is in the center. Okay, and then it would have the toroid on top. Okay, that would be your Tesla coil in the center, and then your primary winding would be around it. And what happens is, let's see how good I can draw. Most often they'll have it, the best way to do it is if it's elevated. If you really get into it, the best way to do it is if it's at an angle like this. So your primary windings are going around like that. Okay, you'll have like you can, some people like make like like wooden, like those wooden brackets at an angle at like a 45, and you lay your winding here, you'll lay it into these brackets, and you'll spin that winding, and you'll have your Tesla coil in the middle of this. You see your Tesla coil is very high, and it'll have all the windings on it. It'll have windings and windings. Your Tesla coil should be solid with windings. That's why I'm just doing this. It's like it's colored in, right? It's going to be solid with windings. Okay, and then you don't have to have the toroid up there. It helps with the performance. It gets a little more technical. It's something I'm not really going to cover that much. It more has to do with like capacitance and impedance. It'll be a better performing Tesla coil if you have your toroid on top, but you don't actually need it to facilitate the act of just getting some voltage to come out. A lot of Tesla coils that you'll see is that you'll just have the end of the winding that you used, it will be at the top, and that's where the energy will come from. Okay, so that is how you'll lay out, and what happens here, and the reason why you can kind of see why, just intuitively why it's better to have your primary angled in this way, right? Because again, air core transformer. So what's happening is that you are positioning the primary windings to kind of increase as the height of your Tesla coil increases, so the energy here has an easier way of climbing up the Tesla coil. Okay, if you just have it all flat, which is the only ones that I've done, really, I've just done flat ones where your winding is just basically flat around, you know, like let's say on a table, and then you have your Tesla coil here. It'll still work. It's just not going to be optimized, right? The most optimized way to do it is to have them, you know, raised up in this fashion, so the primary energy has an easier time climbing the Tesla coil. So the next thing here I'm going to talk about is frequency. What makes a Tesla coil makes it kind of interesting is not just that it's an air core transformer or a high voltage device. The interesting question about this, which I'm sure maybe some of you are asking, maybe that's why you're wondering about it, and why there's a lot of interesting electrical theory involved in this, is that if you've ever noticed, Tesla coils typically don't shock people. Okay, if they're made appropriately and people are using them appropriately, they're not going to shock you. And one of the reasons for this is that the Tesla coil is not just an air core transformer, but it's a high frequency air core transformer. So the only reason one of the only reasons the Tesla coil actually works is because it operates at high frequency, and the reason why it operates at high frequency and it needs to operate at high frequency is because the energy needs to be moving at a certain speed. It needs to be moving basically very fast, high frequency, for it to do the whole, you know, electrical lightning thing. Okay, it needs to be very high frequency. If remember, AC is usually in North America, it's at 60 hertz. 60 hertz is very slow. That's only 60 times a second, right? When you make a Tesla coil, it could be like, I don't know, 10k hertz. You know, it could be higher than that. It could be 100 hertz, 100k hertz. Okay, I haven't made one in a long time, so I can't recall exactly what the exact frequency is. It's probably closer to 100k, honestly. And the reason I say that is because this capacitor is usually in picofarads, so it's very high frequency. So it's probably at the orders of the hundreds of k frequency, because in reality even 10k is not really that fast. So it's probably in the orders of magnitude of 100k plus. Okay. So the reason why this doesn't hurt you is because it's at high frequency. Highest frequency doesn't interrupt or penetrate the human skin as well as a low frequency device would. So that's one of the reasons why if you touch a Tesla coil, you're not going to feel much of anything, and it doesn't hurt anybody. Okay, just like kind of like the globes, the things that you see like a plasma globe, it's same principle as a Tesla coil. The only thing different about the plasma globe, but it has gases in that globe, in that vacuum, and that's why it moves around, and you know, because the energy in there is attracted to those gases, and that's why it moves in that fashion. But it's the same electrically, it's the same principles, so operating the same way. So getting into the circuitry here, let's talk a bit about the circuitry. So we know that it's an air core transformer. It operates at high voltage. It doesn't hurt your skin for that reason, or it's not going to hurt your body for that reason, which makes it safe to operate. But it does ionize the air, and that can be harmful to you. So when you run these, you don't want to be too close to them or inhale, you know, the air that's around it while it's operating for too long. Okay, so we know that, but then we have to cover a couple different things here now. That we get really to the meat and potatoes of how this thing operates and why it does, and that's because of this high voltage capacitor. Okay, and this is one of the most crucial elements of this circuit. You cannot operate this circuit without this component, much less any other of the components in here. And the reason for that is, I mean, this is just a very basic like block diagram of a Tesla coil, and showing you just the necessary parts. This high voltage capacitor is what increases the speed of the electricity coming in. Again, 60 hertz coming in, and we want it to be probably at the order of like 100k hertz when it's coming out. Okay, and the thing is, and that's just initially, okay, because the reality is, and this is why you have a ton of windings, this is another reason why you have a ton of windings on your Tesla coil, is not only to increase the amount of voltage that gets transferred through the air while it's climbing up here, but it also increases the frequency. So the frequency here, it'll likely get an order of magnitude even higher once it reaches the Tesla coil. So you can be even the megahertz range, okay, by the time it gets up to the Tesla coil. Okay, so, and that's another reason why you want to have your winding very smooth, okay, so that it's transferred correctly, and so it increases the amount of your high frequency response. Okay, so this is high frequency. So this capacitor here, and it's just showing you one capacitor. A lot of times it could have more than one capacitor. Okay, it's just, again, this is a very crude model, and this capacitor will be in the order of picofarads. So it's going to be a very, very small capacitor because you're basically making a high pass filter over here. Or if you remember, when we looked through some of those books, I was showing you some of these filters, and we have a high pass filter which looks like this, which is this is R and this is C. You don't necessarily need R all the time, okay? So this is maybe another good lesson in electrical theory. R can be implied. Your resistance can be implied because of the resistance of this primary coil. Okay, so this primary coil could be looked at as R for us. We don't always have to. R is just a value that's going to influence C. Okay, it could influence the frequency response or the corner frequency of your capacitance. But again, we're not getting that specific typically when we're doing something like this, so it doesn't matter that much. Now, if it was a low pass filter, remember that it would be, what's a low pass filter look like? Well, the capacitor would be grounded, and you would have a resistor like this. Okay, and even in the same way, the resistor, the important component in your high pass, this is your high pass, and this is your low pass. The important component in your high pass low pass filter, crudely in a crude model, is really the capacitor. It's not the resistor. If you just put a resistor there, you're not going to get any different frequency response. You're likely gonna, depending on the value of the resistor, you're just going to change, some of your voltage orientation at the certain node in the circuit, but you're not going to get a frequency response change. What's responsible for the frequency response change is the capacitor and the orientation of it. So this is the low pass filter, this is the high pass filter. What we're concerned in this circuit is the high pass filter, which is made by this capacitor, which is in picofarads, because we need to speed up this electricity that's coming out of the wall socket into the transformer and being discharged through this primary winding, and then being picked up through the secondary winding of the Tesla coil, and then we're going to see a bunch of electricity come out here, and it's entertaining. Let's talk about something else. The next important part of this project is the spark gap. So, as you see here, there's another component that we have left that we haven't talked about, and that's the spark gap. It's not necessarily a component, it's just like it's something that's fixed within the circuit to make it operate appropriately. So could anybody think of why we might have a spark gap in here and not just a direct connection? Well, we have to think about the operation of the Tesla coil. The Tesla coil is not a complete circuit. Well, we don't want it to be a complete circuit. We want it, like, it's not a continuous circuit, meaning like the electricity is not traveling continuously. What we want to do is get this capacitor to charge really fast and discharge really fast, which is what it's doing, and that's why it's high frequency. It's just charging really fast. It's charging and discharging extremely fast. Again, at the order of 100k hertz plus a second. Okay, that's 100,000 times it's charging and discharging in 1 second. Okay, this picofarad capacitor. But to help it to do that, for when it to get it to charge and discharge, what do you need? It's like to get something to flow out of a bottle. What do you have to do? You have to uncap the bottle and tilt the bottle, right? So it falls. So the liquid falls out of the bottle, right? You have to do something to encourage it to flow, right? So to encourage this capacitor to charge and discharge, you need what's called a spark gap, which is basically just two nodes. It's basically a short circuit, essentially. It's basically two nodes that are set up within the circuit at a certain distance, and which has to be just played with. Again, we're not doing calculations for this. You can just play with it. It's usually, if it's too close together, then it's a continuous circuit and you're not going to get a good response. If it's too far, then it's going to be too hard for the electricity to want to get to the other side, depending on how much energy is here, right? So you have to play with it to get a good spark gap, because what's going to happen here is there's going to be electricity coming here too. It's going to be dancing, okay? There's going to be electricity here, and typically, I don't know why they did this, but typically the spark gap usually, as far as per my knowledge, would be here, which even I believe makes a little bit more sense. I suppose it could work in either direction, but it'd make more sense to come after the capacitor. In any case, it could just be, just the way they drew it. It should work both ways. But at any rate, what's happening here, it's just easier to illustrate this because it's more linear. So the energy comes through here. You have the 60 or the 150 volts, or 120 volts at 60 hertz that comes through here. It goes through the transformer. It increases in volts. Let's say it increases to 1,000 volts, and then again, that voltage is not good enough. It's like, okay, 100,000 or 1,000 volts, cool, but I need it to be faster. The way to make it faster is to put it through this capacitor. Now it's going to get really fast. Now it's going to start traveling at the order of 100k hertz plus through there. But I want this capacitor to discharge. Every time it does that at 100k hertz, I want it to discharge, and the way I influence it to discharge is I put a spark gap here, and I make that electricity that's charged in this capacitor, I make it want to discharge through the rest of the circuit by completing the circuit here and connecting this node of the spark gap to the rest of the circuit here. Another thing I wanted to mention, because I don't know if it's clear, that alternating AC circuits, when we're dealing with them inside of electronic circuitry or in schematics, there is no line or neutral. Okay, line and neutral is something that comes from the house. Okay, now you can't take your electrician knowledge. Some of your electrician knowledge might screw up some of your like electronics knowledge or electrical engineering knowledge in that respect, because line and neutral is a way things are wired in homes that have to do with safety reasons. But in general AC circuitry, there's both the wires are the same. Okay, there's no, like, this isn't AC1 and this is AC2 or something like that, or this isn't line and this isn't neutral. Now you might see that sometimes depicted on a schematic to show you how the plug is oriented when you're going to plug into the device, but that's irrelevant when it comes to the other side of the transformer. The other side of the transformer doesn't know about this. Sometimes the transformer will be center tapped, and that's a different issue, and there can be a ground there. But this is just a regular transformer. It doesn't. There's energy on both sides, essentially. There's energy on both sides of this. It's not a line or neutral or anything like that. Okay. Because it's not connected to anything else. It's not coming from anywhere else. It's just coming straight AC 120 volts. Okay, and after the transformer, it's isolated. There's something also called isolation transformers. Isolation transformers are just 120 volts in on the primary and 120 volts out on the secondary. So transformers not only do something. That's why transformers are important. That's if you go back in the day. Now, I don't know, people are watching this now. A lot of people might not have any experience with this. But if you were young, and you remember you were young, and maybe you had someone in your family who was an electronics enthusiast or collected antiques, and they had an old radio. If you notice in old radios, like old vacuum tube radios, they didn't have transformers because they were trying to basically save money or making them lighter. They didn't have transformers. But one of the worries and one of the cautions were that you never wanted to touch the chassis of that radio when it was on, because they didn't have any transformers in them. That means they didn't have any isolation. Okay, so transformers not only transform your energy, but they also isolate your energy. And if you ever see an isolation transformer, that's what, like, if you wanted to take a step up, let's say if you're in your house and you're worried about lightning strikes, and you're worried about not blowing up your television or your video game console or your computer in your house when there's a lightning storm or there's a surge in the power, and you think your surge protector isn't sufficient enough to do that, well, the reason why it's not sufficient enough is because a surge protector is basically just an automatic switch that says that if it feels a certain amount of electricity, usually in the order of like k volts or something, if it feels a certain amount of spike in the electricity, it will shut itself off. Hopefully in the order of microseconds, it'll shut itself off, and it'll prevent that pulse of electricity from going into the rest of your electronics. It doesn't isolate it from anything. It's just an impact switch, right? It's just a fast switching impact switch that says, hey, if I feel this, I'm going to shut off as soon as I feel it, and hopefully that will save your electronics on the other side of that. Okay? If you're not that comfortable with that, because again, now they're getting faster, but the worry is that you don't know if it's gonna switch off fast enough to save your electronics. So you can get an isolation transformer. An isolation transformer will do exactly that. It's just 120 in, 120 out, and it'll have some kind of amperage rating. And that is the best way to protect your stuff, because it has the transformer in there, that core, and that makes it so that this line is completely physically disconnected from this line. So anything that's irregular that happens in this, just drawing, that's you typically never seen a sine wave do all that. But let's say a spike is usually going to look like this. Let's say, okay, I'll do it. Let's be responsible here. So if I have let's say if I have a sine wave, or regular sine wave, and then that's what some kind of lightning strike or something's going to look like. It's going to look like a really sharp peak that happens. Okay. You see those really sharp peaks? What's going to happen is that this transformer in the middle, it's not going to let me feel that, or at least not as aggressively. It's basically going to smooth that out and isolate me from all those irregularities, because it's a fixed core transformer that's not connected physically to the wires on this side, right? Because it's basically every transformer is an air core transformer to a certain degree, if you want to say and get technical, right? I say you call it iron core just because iron's in the middle of it, and that's where the coils lie. But all of the electricity in a transformer gets transformed through electromagnetism, not through connection. So this is just going through the air in the spaces of the transformer. So no physical connection here means that even though while I have erratic signal on this side, I'm going to get clean, consistent signal on this side that's going to be void of any inconsistencies. Okay? So isolation transformers are going to be used in hospitals a lot. Most of the stuff that's connected in hospitals has isolation transformers. You'll notice that if you look for isolation transformers, they're going to be very expensive, and one of these reasons why they're very expensive is because they're large, and the reason why they're large goes back to what I was talking about earlier, is because they're usually high current. Because what's the typical current of an outlet in your house? It's going to be 15 to 20 amps. 15 to 20 amps of electricity is a lot of electricity. Okay, so you have to have thick wires. When you have to have thick wires, that means the coils on your transformer has to be thick enough to carry that much voltage, and that means it has to be large to carry that much voltage. Okay, so isolation transformers are usually expensive because they take a lot of material because of the size of them, and they're usually very large and heavy, very heavy. I actually have one here for the flight simulator, and I'll probably show that to you guys someday. It's a marine isolation transformer, and I'll probably show you that to you guys someday. But yeah, I'm not happy about having to move it around a couple times that I have to, but you know, it's large. So that's the in and out of your Tesla coil. That's what it is. So I actually do appreciate the person that mentioned it, because it's actually a pretty educational circuit. You know, a lot of good useful information and a little electronics theory to learn from. It's really cool. I think I would encourage you, if you're looking for an initial project, a first couple projects, I would encourage you to get some materials and make a Tesla coil. It's very simple and interesting, and it doesn't take a lot of components, and it's more on the electricity side of electronics. Okay, this is not as much electronics as it is electricity, so you can learn a lot of theory behind what goes on in electricity with this circuit. I appreciate you guys watching. I'll see you soon.